for coming out. Sorry we were a little late. The traffic was crazy. Like Sharon was saying, I work at GigaSpaces. I've been doing some possibly interesting work, orchestrating Kubernetes on stack and really in a hybrid environment, meaning we started a project some time ago to really stress our orchestration product so that we could orchestrate the deployment and operation of Kubernetes itself, as well as coordinate its deployment with external services that were not in Kubernetes. So and I'll get obviously into the details here. This is going to dive pretty deep, pretty fast. So hang with me. Got a lot of detail here. It's very much a real world effort. So this is not abstract. This is something I've already done. So this is more of almost a lessons learned. And so I'll describe that again, not just Kubernetes, but Kubernetes and non-Kubernetes in a hosted services. So how many here are familiar with Kubernetes at any level? So some 50-50. Okay. So I'll give an incredibly brief description of Kubernetes. How about containers? People know container from a VM. Okay, and then the ultimate goal of this project was to take Kubernetes and non-Kubernetes services and orchestrate them in a way that microservices deployed in Kubernetes could be scaled automatically based on metrics in a hybrid environment where the microservice was actually connected to a service that was outside of Kubernetes. So the scaling of automated scaling of services in Kubernetes, which originally wasn't even available in Kubernetes. There is an auto scale capability in Kubernetes now that wasn't when I began this. And also Kubernetes itself and all the services. So it's very much about not only the deployment part, but the post-deployment dynamism. So to be able to respond to workloads and stuff. Okay, so here's the Kubernetes education. So it's container orchestration. So it's very much focused on just coordinating the deployment and operation of containers, Docker or Rocket. It has a pretty basic architecture, really, master minion type architecture. So it has essentially one controller process and a bunch of workers. And the workers are actually just host the containers that are deployed into it. Containers are really considered immutable from the purposes of Kubernetes. So it's not like you create an empty container and then load it up with stuff. The idea is that you have containers out there that can be downloaded. They're pre-prepared, and there's some customization available via environment variables that I use anyway. There's a concept of a pod in Kubernetes. So in Kubernetes, a pod is a group of containers, and they share the same network namespace. The pod in Kubernetes is the unit of scale. Okay, so if I tell Kubernetes to add another instance, and there's a command for that in Kubernetes, it will replicate the contents of a pod. You can't replicate half a pod. All right, so and that's meant to keep service locality. So if I have, like in my example that I'll go over, I have a container that actually contains a metrics collector that's sitting with Node.js, and they just get deployed as a pod. So anytime I scale, I get another one of both. But it could be anything that you would want to be grouped together that's always going to be on the same physical hardware. Because otherwise you don't know where you can control where Kubernetes does placement, but it's things that you will not guarantee to be on the same physical box. There's a concept of a replication controller. So there's an external process in Kubernetes that's responsible for scaling pods and also ensuring that they stay scaled. So if I say I want 3 of these whatever they are, 3 Node.js instances. Kubernetes scales it, creates the additional containers that are needed, deploys them into the various minions out there, or nodes as they call them. And then it also keeps watch, so if something fails, it'll bring another one back up. Okay, so that's the job of the replication controller. Then there's a concept, the one thing about the pod that's interesting too is every pod is assigned an IP address, a fixed IP address. Because Kubernetes has an overlay network they put over their entire cluster. So this allows you to actually have, essentially treat a pod as though we're a host, even though it isn't. So a pod almost does become like a VM in a way, because it gets an IP address. Then there's the concept of a service, because even though each pod may have its own IP address, that's only within the context of the cluster. To get something that's visible outside, there's a concept of a service, and that gives you an IP address that's externally visible and lets you basically perform a sort of load balancing across your pods. So it gives you a single point of access no matter how many pods you have. And since one of the ultimate goals of this was to create a scalable, an auto-scaling system based on TOSCA, which we'll describe later, we needed all of these concepts. You could use Kubernetes with just a pod. You wouldn't have to have replication controllers or services or anything else. And then the kube control utility, this is sort of the master utility. They have a REST API as well, but I found it impenetrable, at least on the time scale I had. So pretty much when I'm doing the orchestration in Kubernetes, it's using this utility. And so that's how you basically issue commands to Kubernetes, tell it to deploy things, to scale things, and so forth. Okay, so there's just a visual representation of that. In this case, so we have a replication. There's no service here. Actually, I should have another box out here with the service. But the replication controller is sitting on top of a node. Okay, and the node has a pod in it. Okay, with a JBoss in this case. So 2 pods under a replication controller. If I told the replication controller I want 3, yeah, it would stick one here maybe, or maybe we would put another one here. So we would have 3. Okay, so here was the target architecture for this project. So visually, to make it a little easier to understand. So all on OpenStack note in this case. And actually there's nothing about this project that was tied to OpenStack particularly. I mean, that's just the cloud, the preferred cloud that I'm working with. It's really the same principles are apply to anything, including hardware. Physical hardware or AWS or whatever. Doesn't matter. So the basic idea is I have Kubernetes. I have a master and some number of minions here. I want to be able to scale Kubernetes itself, perhaps add capacity to Kubernetes, because each one of these minions is on a virtual machine in OpenStack. If I want to add capacity, I add another one, and that becomes another pool that Kubernetes can deploy containers to. So it'd be nice to scale Kubernetes. And at the same time, I put Node.js here. So this is just a little background. We have a kind of a standard hello world type application for a Cloudify product. And it's the old standard Node seller for Node.js. So it has a Node.js front end and a MongoDB cluster. And it's supposed to be like a wine cellar application, like a wine store. Like this is what it simulates. So essentially, this Node.js is a web server in front of this Mongo database. Okay, so the concept is here that I'm going to take that microservice, meaning Node.js, deploy it into Kubernetes, be able to scale it inside Kubernetes, and have Kubernetes orchestrated this service, this Node.js service, orchestrated to talk to the Mongo cluster that's outside, and do this in some way that's understandable to some extent, comprehensible, repeatable, and so forth. So this is kind of a list of steps of sort of what you're up against when you try to tackle this problem. not related to any particular tool set or whatever, but just the idea of what do I have to do? I have to create Docker containers for Node.js and metrics collection. I have to do metrics collection because that's how I want to auto scale. I'm going to auto scale, in this case, based on the number of connections into Node.js. If I get above some arbitrary threshold, I want to add another, I want to tell Kubernetes, give me another pod, and that will create another Node.js instance and reduce the load, basically. Then I need to instrument the containers to configure external. So those containers, when they go in, don't know where, for example, Node.js doesn't know where MongoDB is, right? Because it doesn't exist yet. And MongoDB is outside Kubernetes. It's going to get assigned an IP address when I bring up the VM that it's on to go to install it. So somehow I have to feed this stuff in. I also have to feed into this the metrics collection process, which we are using Dreamin, which is an open source metrics collector. I have to tell it where to push the metrics to. So then it's all be dynamic. Then I have to create a replication controller here, service descriptor templates. This is a Kubernetes thing. They have a YAML format for describing the contents of a replication container controller, for example. So it will basically list the containers and some of the options you want. Okay. And then I'm going to create a Riemann configuration for threshold detection. So Riemann being the real-time event processor of choice for this project. So it has to be receiving the events that are flowing out of this, and then it has to cause the scale. So this is all the preparation part. Now for runtime, I have to create network subnet router for VMs on Openstack. I have to create VMs for Kubernetes and MongoDB on the network. I have to create a VM for the Riemann event processor, deploy Riemann, blah, 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 right? Save the Kubernetes Mongo IP ports, install MongoDB and Mongo VMs. It goes on and on. Set environment variables in the replication controller template. If you recall, that was the way you can customize the containers before they come up. That's how you pass in external information. So, okay. And then I'm going to copy those rendered templates, meaning this replication controller template. This is the Kubernetes native descriptor. So what I'm going to do is do some substitutions on it with the values from that were discovered up here, like these ports, the IP import from Mongo, the Riemann IP import. And I'm going to plug that in there into that template, and then I'm going to actually copy the template to Kubernetes master. I'm going to call kube control to actually launch Node.js and cause the metric collection to begin. And then I'm going to use kube control on the master to create a service endpoint. Okay, and then I'll actually have an IP address I can go hit, and then we'll go talk to the MongoDB that I started up, and presumably if I get a sufficient number of connections, a miracle will occur and the Kubernetes side will scale. Okay. So there's a lot of steps. No purpose of listing this, which is really just fills your head with nonsense. It's really, the purpose of this is to give you an appreciation. It's only a partial list, just an appreciation of the complexity of doing this and doing it in a way that's cloud neutral. It's a lot of work. When the threshold is reached, execute the scale. When Kubernetes runs out of space, scale Kubernetes, blah, blah, blah. Wrap all of it in retry logic, its failures, so its timing. The cloud is much slower than Kubernetes, all of that stuff. So automating, it's a lot of work. It's very complex and error prone. Yeah.
When you add minions or pods, we create new VMs, right?
No, you don't. So
In Openstack,
if you create a new minion in Openstack, you put it on a VM. If you're doing it on OpenStack, you have to create a VM. So the VM is the node, and then the replication controller may put several instances on that one, several instances of the container on that one minion. But yeah, if you want to add capacity to Kubernetes itself, you have to add another VM in OpenStack in this or whatever cloud you're on. So I already talked about that. Okay, so the approach, that we take, that we obviously at Cloudify, GigaSpaces are backers of, is TOSCA. So it's an introduction to TOSCA modeling. Has anybody heard of it here? Okay, so there's a few. Okay. So TOSCA stands for, it's an OASIS standard. It stands for topology orchestration for cloud applications. It's not really that. It's really, it's more general purpose than cloud. It really has nothing to do with cloud per se. It's the most likely use case for it, but it's really the application orchestration period, whether it's going to go on a cloud or any other target infrastructure. That's not really the important part. The important part is the way it decomposes or describes a model of a deployment, of a complete deployment. Now, we're not talking about the deployment for like a chef or puppet on a single node, but the entire picture of your deployment, including the network, all the VMs, all the application software, and so forth, and all the relationships between them. So this is how, the approach to this problem is to build a model. Models are a directed acyclic graph of nodes, basically. So node in the mathematical sense now. So we've overloaded node 3 times. It's not a compute node. It's not the Kubernetes node. It's the node like in a, math. Yeah. Okay, nodes are anything that need orchestrating. Hardware, software, VMs, containers, networks, floating IPs. Beyond that, they can be just pure logic. It can be just something that needs to be executed, even if it doesn't actually cause a change in the underlying infrastructure. There's actually an example of that later. And then all the nodes are connected by relationships. The relationships actually are not passive, so they actually have code associated with them. I'll talk about that a little bit. So this is like a generic example of a TOSCA model. The idea is you're going to have types. TOSCA defines a type, sort of a meta-type system. So a system for defining types, ultimately, but each one of these would be a node. Perhaps a VM would be a node, and you would have connected to a subnet, and it would be contained in a network, and connected to a floating IP, and so forth. An application would be contained in the VM. So an orchestrator applies workflows to the model. So now we're getting kind of into runtime of the model. So the first job is actually to describe the model. Second part is to actually do something with it and apply a workflow to it. One workflow, for example, is install. Right? Another one would be uninstall. Those are the most basic workflows. But it could be anything. It could be update the software on all of the web tier nodes. So TOSCA also, the type system is very flexible, lets you define custom types. The types ultimately get tied to some kind of code that gets executed. So, if it's on a particular cloud, that code might be the, for example, the OpenStack API, Neutron or Nova or something, or it could be AWS or something completely different. It doesn't really matter. The model doesn't care about that, actually. But the type will tell you, types have a certain, naming convention that gives you a sense of what they are. It'll be an OpenStack floating IP, and so forth. And then this is just an example, a server node for OpenStack, so defined operations needed to operate, Neutron, blah, blah, blah. Okay. So, to take this into something more concrete and then maybe just make it easier to understand the TOSCA process, this lead through kind of a process of defining this system that I described. So the first, one thing that has to be done is define custom types for Kubernetes itself. So that was one of the things. I might define a type for master. I might define a type for minion / node. Node is the proper terminology. Define operations on these to configure and install. And then probably, I might actually delegate the actual install to some other tool for that, more custom built for that purpose, or maybe not. And actually, in my case, I just scripted it. the end. So in the end, the model looks something like, you know, I have a couple of VMs here. The node, these are sort of the workers and the master. The masters contain, the master here refers to the software. So this is the actual, you know, Kubernetes code here. That gets installed on the master VM. Here's the code for the node VM. And then there's a connection between the node and the master. And then custom types for MongoDB, for example, I would have MongoD and MongoCFG and MongoS. And if you don't know MongoDB, it doesn't really matter. Those are all components of the Mongo cluster. And define operations on these, same basic idea, and the same pattern applies here. Okay. And then probably it gets more interested is define a custom type for a generic microservice. So this is the case where this type isn't, I'm kind of giving this away early, but this type doesn't actually have anything on the cloud. There's no VM for this, because this is just going to be described something that gets pushed into Kubernetes. But that has a whole set of logic associated with it that I described before. Like, I have to have an associated set of Kubernetes descriptors. I have to somehow override that with the real values from this deployment, like the Mongo IP address, the Riemann IP address, and so forth. So, you know, there's logic to be done, but there's no VM to do it. So it's not a requirement in TOSCA that be the case. So the complete model is simplified if we assume a flat network, which I did anyway. Why not? Master VM, right, connected to, this is the same drawing that was up there before, and then we have MongoD that's external here. This is, of course, Kubernetes. And the relationships, you know, here runs in, that's not a real TOSCA relationship, but it doesn't really matter because it's the concept. But we're going to run a workflow on this, and the workflow, for example, install is going to use these relationships to determine the order things start in. So a standard workflow, it'll actually, so when we go to actually render this on a cloud, the standard workflow will actually walk the model and figure out which nodes are independent and which are dependent. And the independent ones immediately go. So it's going to look at this and it's going to say, you know, the VMs are independent. They don't depend on anything else. Everything depends on them pretty much, except for the microservice. So they immediately start getting deployed. And when I mean they start getting deployed, there's an orchestrator. Obviously, the Cloudify is one such orchestrator, but the orchestrator in TOSCA is what actually acts on the model. So that's the job of the orchestrator, is to do this and activate the relevant code. So it's going to immediately deploy these VMs.
Where are the apps?
The apps are still, well, at this point in time, or you mean in general? I mean,
like you say, this is the complete architecture.
Yeah. No, this is master. Okay. This is the actual Kubernetes code. Okay. So this is the actual Kubernetes code. This represents the Mongo code, which in reality, the actual process of installing this might actually be just SSH out to this VM and download stuff. It doesn't really matter. But that represents that, and then the microservice represents the actual Node.js. Okay.
The wine cellar.
Yeah, exactly, the Node seller app. So and also the instrumentation, so so this it's kind of hidden here. The microservice, if you recall, points to the Kubernetes descriptors. Basically, it says that type has a couple properties in it that say, okay, you know, here's the list of Kubernetes descriptors I want to deploy, and I'll show you the code for it later. And here's what I need to replace in there with the specific values, you know, like the IP address of the Mongo VM. so forth. Okay, so once we get past that step, the VMs have come up, and now the next set of independents to be done, right? So master and Mongo now have no, they're independent once those guys are up. So they get installed also in parallel. Now the last independent set can be done. We're going to install a node and the microservice can go because the node was waiting on the master in order to be up because that's the way you have to do it with Kubernetes. Okay. So there was one thing I noticed in the description of the talk was, cloud portability was one of the topics. So I just wanted to have a little aside about cloud portability with TOSCA, for example. There's an urge in the world out there to write an orchestration once and then have it just pointed at whatever cloud you want, and somehow magic will happen and it'll just work. This is largely a fantasy because unless you have something extremely simple that you're deploying, the clouds. It used to be even worse, but they don't have similar capabilities, and sometimes the capabilities aren't translatable between them. So you might have a certain cloud has a very fine-grained ability to manipulate, to do like SDN, like Openstack, and then you might have AWS, which is less flexible. And there's some things you just can't do the same way, so it doesn't make sense. So you can approach that in 3 different ways, really, that I can think of anyway. You can have the abstraction approach, which means I'm going to take the least common denominator of all features, and depending on how many clouds you're interested in, if you do them all, maybe all you wind up with is the ability to launch a VM or something, right? But on the other hand, if you have like 3 different targets that are pretty similar, then yeah, you can probably do it, and you might create a custom type in TOSCA that just does, that sort of provides like a facade over those other cloud APIs and just does a little simple translation. The other way is pluggability. Okay, so you're going to, in your model itself, you're just going to have different types for each cloud. All right, and when you go to another cloud, you're just going to substitute in the other types as much as possible. And like I said, it's not always direct. The clouds aren't necessarily isomorphic. Like so here, in other words, you can't necessarily transform. You can't do the same thing on every cloud. So this is really the most flexible. It doesn't give you the joy of writing once and never having to change anything again. But it's more realistic for the real world. And then there's a hybrid, which is sort of what I described before, where you actually write a facade over the top of the plugins, so you can do that too. So there's 3 different approaches. For Cloudify is the pluggability that we found was most effective because we found that the flexibility in the real world was never support this. This was actually the road we headed down in the first early versions of our product. And then, we had a major rewrite for version 3.0 that went to pluggability. So any of these are possible. Okay, so here's
Which
the.
does it support? Which clouds? Which cloud does it support?
Oh, well, we have we have Amazon, OpenStack, let's see, software, most of the major ones. I can get you a list later if you want. Azure is 3.4, which is like middle of this year. So this is just an example, a concrete example of actual configuration. So the configuration in Cloudify. So now we're kind of moving into a little bit into the Cloudify world. And Cloudify uses the TOSCA inspired structure, so it's YAML. But here's just an example of a equivalent node type between 2 different clouds. In this case, how that's actually expressed. So like I said, TOSCA, you have basically an inheritance hierarchy like an object-oriented language. Right? So you can have operations. In this case, your life cycle. You can. So there's a root, So any node in Cloudify, for example, is going to implement these operations. And here you have security group. It's a generic tag interface. It doesn't do anything for some reason. And then over here, we have the Openstack security group, and it has specifics and specific, you'll note here, implementation even plugged into it. So it has specific properties that it's added, and it has a specific implementation. This is actually pointing to a Python package implementation, which calls the Openstack APIs. And ultimately, in the way this works is that the properties you set in here get passed into the API calls. So they sort of act as a way of allowing you to access these cloud APIs without knowing the cloud APIs. You simply pass in the parameters in the form of properties, and then the operations take care of, for example, when it creates stuff, it'll go do whatever it's needed to do. And similarly for AWS security, there slightly different descriptions on how to set up the rules for the firewall. We're talking about security groups. And of course, it has a different implementation. This is going to obviously go to the Amazon API. So, all right, so now we're getting down to the guts, the Kubernetes server VM definitions. This is an example definition of a VM. So inside of a blueprint is what the TOSCA terminology is. You can have for example, you have a host, the master host. This is the host, the VM that's actually going to have a type. Openstack node server. It's going to have a certain number of instances you want to deploy. It's going to have some other, ignore that one, but it's going to have an image and a flavor from Openstack. So these are being passed into the orchestration at runtime. It's got some flexibility like that. And then it has some relationships. And in that drawing, I had that before, for example, it's a security group. And under the hood, Orchestrating uses, I already said that, constructs the proper Neutron Nova API calls. Same concept applies to the Node.js. In other words, you have the same, actually Mongo, I should say MongoDB. This is an example security group definition inside of a orchestration. So you actually are setting the firewall rules here, and then there'll be a relationship between the VM and the security group. And when the orchestrator observes that relationship, it will see that, for example, the security group won't be dependent on anything. So it'll create the security group immediately. And then because the server is connected to it, it'll actually execute the proper Nova calls. I think that's a Nova call, right? Nova call to connect the security group to the VM. All right. So now we're digging into the microservice type here a little bit. What's interesting here? So this is essentially what it's got is properties that are needed for the kube control commands. This is the Kubernetes command line command to execute. So it's, the number of replicas you want, for example. There's this is just kind of a catch-all, so you can pass overrides to Kubernetes. But ultimately, these all will become options on this Kubernetes command to start the actual containers that we need for this. Okay, and then it's got these life cycle. This particular interface is recognized by our orchestrator. And is what the orchestrator looks for. So any implementer of this will be deployed. For example, during a install operation, all that happens is the orchestrator goes through the tree of nodes, looks for everything that implements this, and then whatever is defined for start, it runs. And this is just Python code. So in this case, it's a custom little piece of code that actually SSHs out to the Kubernetes master node and runs the microservices that we want. and that's going to get started. And again, this is the microservice node, which has no actually runs on the orchestrator. It's just pure logic. It has no actual VM that it runs on. That's what I'm getting at here. It's simply automation.
So you must have opened the
If you command the minions, you command the master. So actually, once the Kubernetes cluster is up, the only thing the orchestrator cares about is the master, because the master is where you command everything. So after that, because remember, this is kind of a nested orchestration, right? It's an orchestrator that's commanding an orchestrator to orchestrate. So from that perspective, from the perspective of the, in this case, Cloudify, from TOSCA's perspective, the only thing it cares about is what it needs to give commands to, and that's the master in Kubernetes. And so when this install comes, this is going to actually take the defined Kubernetes deployment specs, substitute the runtime values, SSH to the master, and start everything up. And this is what I just done. So this is actually a look at it. And this probably the only thing interesting here is the config files proper. This is a custom type that I wrote, so it's not standard or anything. But, Kubernetes, you have to have a separate file. There's one file to define the pod, which is the pod, which defines the two containers that we want. And the containers are just uploaded to Docker Hub. Kubernetes will, by default, download from Docker Hub, where you can point it at your own private container repository. And then here, it's basically what it does is slurp up this YAML into an internal map of maps, basically using PyYAML. And then all it's doing is then just substituting values into it. And here, this is just some special syntax for putting like the Mongo IP address, the Mongo port, other things. So then it does that substitution and writes it out, and that's what it uses to command Kubernetes. This is the Kubernetes native descriptor. So this is Kubernetes stuff here. This is not GigaSpaces or anything else or TOSCA. So this is what an actual Kubernetes descriptor looks like, and this is where we've got some things in here. Notice the environment. This is the key, really. Besides telling me here's the image I need to grab for node seller, or here's the image I need to grab for Diamond, which is going to do the metrics collection, right? So I've got two separate containers, but each one of the containers has an environment, and that's basically what I'm substituting with those previous commands. So that's going to feed the runtime information into Kubernetes. When these things start, they're going to know, how to connect to Mongo, how to connect to the Riemann. Okay. Let's see. Yeah, I already said that. And this is just an example. Inside the container itself, the Diamond container in particular, just run when it starts. One thing you command with Kubernetes is you tell it, you tell it what to run after the container is actually deployed. So in this case, it's just the start of scripts that are sitting in the container. And they just activate a little Python script that, in this case, for the Diamond collector, it actually just edits the configuration with stuff that's pulled out of the environment that we passed in. Now the service metrics approach. So we're getting, I'm sure you're filling up, but we're getting near the we're getting near the end, or at least past the middle. So we still need to gather metrics somehow. So this is just the details of how the metrics actually get gathered, or how that's configured. So the scenario does require that I get metrics from Node.js, because that's what I want to demonstrate scaling here. So how do I do that? I have a Diamond collector container. It's in the pod of Node.js, and this has all been expressed already, I think. And it's pretty much I'm passing the target host and the information for the queue. This is kind of probably too much detail. Riemann has a certain syntax. Events have to have a certain attribute. There's a certain pattern that you have to name events, and that's part of the configuration process. But the main thing is just to make sure that the collector knows where to push the events to. Okay. And it sends a number of connections in the local pod, and Riemann evaluates the metrics. In this case, it's a simple threshold. It's got a sliding window. When the number of connections exceeds a certain limit, it will trigger a scale. Okay, and the way it works is the Riemann actually tells the orchestrator to scale. Riemann itself is just processing events, so it doesn't. And also Riemann, you can't do anything that takes time in Riemann. It's very sensitive to doing latent operations that are latent, high latency, so you can be quick. So it just issues a command back to the orchestrator once it's set and says scale it up, and the orchestrator takes care of scaling it up. Now, under Riemann. So what's Riemann? It's high-speed event processor. It's written on the JVM enclosure. It keeps a minimal state, really just the last sample of every event. It doesn't keep a database of events. It's not a time series database or something. Its only job is to get events and take some action on it. Now you can define streams, which are really just high order functions in Clojure. And those functions can maintain state. So that's sort of how you can have things like a sliding window. You can basically close around the data structure and inside the function and fill it up with whatever you want. So if you want to collect, an array of 10 items, you can do that. Riemann itself has an API. Again, it's Clojure, but they have a nice API that basically serves sort of a DSL for writing these metrics collection things. And it has most of what you would ever need without doing too much. And let's see, get past that. So this is scary, right? I don't know if anybody knows Clojure here, but it's Lisp. It's common Lisp, but this is what it looks like. And basically, in this case, the events flow in. The important thing here, this section here, is just essentially counting the number of hosts that are at any point connected, and down here it's saying when it's dividing the number of the average of the slightly this moving time window here. So it's got a moving time window. This is something that Riemann provides. A lot of these functions are not closed Riemann API. But it's saying over this moving time window, take the mean or the average across it, and then down here I divide it by the number of connections globally, by the number of hosts that I detected. If it reaches some threshold, it triggers this, and this is the most important line in here. Process policy triggers. Okay. Process policy triggers is it's a function that Cloudify puts in the Riemann environment, and that's really the way that the orchestrator is told to do something. So and that's done asynchronously from a thread pool, so it doesn't slow Riemann down. It basically just fires and forgets it. It keeps chunking away at things. It's got a cooldown period and other cool stuff. Okay, so now we've gathered the metrics. Again, the recap, so because we've already got lost during all that. Containers are prepared for the pod, the replication controller. The orchestrator feeds connection information from Node.js, Mongo, and Daemon to the Daemon collector to Riemann via the environment variable, or via the environment and the Kubernetes descriptors. Orchestrator edits the descriptors, tells Kubernetes to start things up. Node.js connects to Mongo based on those values we stuck in. Daemon connects to Riemann, which is metrics. And then Riemann commands the orchestrator, which is a workflow, to scale Kubernetes. Okay, so takeaways. TOSCA makes complex orchestrations. I was going to put understandable. I said more understandable. It's more understandable to build a static model like this than it is to write a bunch of scripts or to try to hack something together with other tools. So it makes it very clear what depends on what. It encapsulates code in the types so that the boundaries of control are very clear. It separates the model from the actual execution of the model. It separates even the types in the model from the particular target, whether it's hardware, software, cloud, virtual machines. vSphere is another one we do. It's not even necessarily a cloud, vCenter. And orchestrator can coordinate other orchestrators. There's really no limit because ultimately what the orchestration is doing is the types really just represent blocks of code that represent different life cycle events in the orchestration. It doesn't, they're not tied to any particular technology or any code. They could do anything, right? They could do nothing. They could do, you could run it on hardware, you can target existing physical boxes or VMs or anything else. Okay, and that's the end of that. But I did have a little, just proof of the pudding. I have a little recorded demo here.
Connected to the Wi-Fi? DeWayne?
Huh?
Are you connected to the Wi-Fi?
I don't need it.
Oh, you don't need it?
No. It's just sitting right here. Yeah, but I have to stand over here. So I just want to. This is a Cloudify orchestrator, the UI for it. So this is where the way this was ultimately orchestrated is with 3 different blueprints. So one blueprint that's here to that actually started up Kubernetes, independent of anything else on OpenStack. This one to start up MongoDB, also on OpenStack. And then the demonstration was the installation of the microservice, which refers to these other running orchestrations.
So there is a third orchestration?
There's a third orchestration. So now the reason for this, there's actually a story behind this, because this was this wasn't like some master plan. It sort of evolved over time. But originally this was all in, and there's no reason these couldn't all be in one orchestration, one file, basically. But the whole philosophy of Kubernetes is around microservices. So you want this agility to be able to just deploy microservices and undeploy microservices as needed and add them, scale them independently. If you have it all in one file and I say undeploy, or uninstall, it's going to uninstall the whole 9 yards. Mongo's going to go away, Kubernetes goes away, the that's not the idea. So eventually it was broken up into 3. So that the microservice sort of with a special proxy node that I wrote actually connects to those other orchestrations and operates them as though they were in the same blueprint, but it's independent. So let's watch what happens. And I know what's going to happen. Because it's not a real demo. It is a real demo. Happening now. All right, so let's see here. All right, so now I'm bringing up, this is a tail demo, basically. So this is a tailing demo. This is the output of Riemann here, and once the right now it's not operating. It just says shut down here. When the orchestrator deploys creates a deployment, it also creates a special core in Riemann process events for it. This is the actual CLI for Cloudify here, and this over here is the Kubernetes master node. Okay. So one thing to show here. Oh, that's it. Okay, so the first thing I did was show here. Basically, I'm executing a kube control get RC. So that's just kind of a generic command to say list all the replication controllers that are running on the Kubernetes cluster. It comes up empty because I don't have anything running. All right, and then I start the deployment in the middle window. Start running Kubernetes deployment, and we discussed earlier how the orchestrator organizes the tasks. So in the case of Cloudify, we use a celery task broker. So it's doing, we basically assemble a tree of tasks, and celery takes care of going off and running everything parallel. So it's going through all this. It's connecting to Mongo. Okay, and now it has come up. This is showing the Kubernetes deployment. Oh, this is showing the Kubernetes deployment in the UI. Okay, and we can start to see events flow here. And over here, I think. Yeah, over here. So right now we're getting a connection flowing. So here's the host. This is actually the host in this case is the actual private IP address assigned by Kubernetes to the pod. And this is the number of connections. This is the count of hosts, the running count of hosts. Right? So that starts to flow. The metrics start to flow, and we see the number of connections. It's kind of a long story, but the number of connections is gradually increasing here. You see it's going from 6.5 to 7.5. It's fractional because it's averaging across the sliding window. All right, and it gets to 10, and then it's yeah, and then the scale happens. That's this output here. So right, and that triggers the workflow on the orchestrator. And then you'll notice over here on Kubernetes now, there's 2 replicas. So anyway, that's that was the fruit of the labor. Right? So, and basically, if you let the number of connections drop, you can scale it both directions or run arbitrary workflows. So server side stuff is not that sexy to watch the counts go up and down, but the big takeaway is the ability to model a complex orchestration like that, where the orchestrator is doing arbitrary logic, manipulating Kubernetes, microservices internally, as well as potentially scaling Kubernetes itself, even though I don't show this in this particular demo. And theoretically, you could scale Mongo too in the same orchestration. So, any questions?
So was this done for a customer specifically just as a proof of concept or as a future product to support Kubernetes better?
Yeah, I mean, it's more, it wasn't done for a specific customer, so it is going to be part of the, it's going to be baked into the product, but it is, it's partially just the hybrid cloud orchestration story. It's a very hard problem to solve. But it is going to be baked into the product as a plugin. There'll be a Kubernetes plugin so that, because the sort of the operating theory is that most people using Kubernetes are not just using Kubernetes. They still have to orchestrate things. They may use it precisely in this type of situation, like a microservice architecture for the web tier makes a lot of sense. Maybe not so much for your heavy database server or something like that. Usually not going to be functioning, operating that like a microservice. So you may have both in an environment, and it's really, this could be Mesos. It's sort of like a demonstrating the whole concept of being able to handle flexibility of the tool, being able to handle orchestrating an orchestrator, like orchestrating anything, I guess. Like you can't think of anything crazy enough that we couldn't orchestrate. Sort of.
Do you have many customers with Cloudify looking for this ability to orchestrate orchestrators?
We have a few, It's not the vast majority. It's sort of a cutting edge feature. I mean, most people have rather mundane orchestration needs like anybody else, but they're not quite, most people aren't thinking that far ahead. But this is kind of, out there. But the level of automation, it's, attainable, which is very hard to do by other means in a standard way. So the product's open source. The orchestration language is a standard, so it's it's not a sort of a vendor lock-in type situation.
Why was Riemann chosen as a glue? Was that because Kubernetes didn't have its own auto-scaling stuff?
Yeah. Yeah, well, actually, I don't even know the backstory. So Riemann is delivered as part of, for the purposes of this demo, Riemann is built into Cloudify. So when you get a Cloudify server is a marriage of a bunch of open source products: Elasticsearch, InfluxDB, Riemann, some others, RabbitMQ, and well, it goes on and on. It's got quite a stack to it. So that's really the rationale of using it.
You just had it handy.
Yeah, I had it handy, and it's in the product, and after all, I'm writing this for the product, so it makes sense. It's it's a very general purpose tool for doing event processing. So it doesn't limit really. You could push any kind of metric into Riemann, and cause even from external to the orchestrator if you wanted to, you can push something in there. Some event that indicated that there was going to be a system outage or something, or to, I don't know, maybe manually scale something even.
You make it every refined.
Yeah. All right. It's straightforward, really, and very flexible, and also open source. Again, everything we had, because the product's open source, all the components naturally had to be open source, and that's a leading open source real-time event processing engine. Nothing else. Yep. Thanks for coming out.